I'd like to welcome everyone to our second in a series of LED videos being presented to you from General Electric. We are located at the Institute in Cleveland, Ohio, and Current, powered by GE, is happy to present this new information to you. This is the second of our videos. Our first video was on LED basics, and as we move forward building this library of videos, I'm hoping you find these to be helpful and informative. My name is David Korow, and I'll be your speaker today for our video, LED Reliability Life Ratings. The video is made up of many different parts. We'll be covering a lot of different topics, and this slide is really intended to let you know what the content of the video is, as well as the begin and end times for each segment, so that you can go back and review any topic in the future that you might find of interest without having to search the whole video to find it. LED reliability is a big topic, and being able to separate out the better from the best is important to all of us. Our monies are hard-earned, and our time is very valuable, and by choosing the proper solution at the proper price for the given application, we can get the best benefit possible for our investment. One of the big questions that's out there is, what does L70 50,000 hours mean? What do these life ratings actually mean, and where do they come from? And that's really what this video is about, and we'll be exploring that topic in detail. We're all familiar with cut sheets. What information is available? What's important? And most importantly, what information on this cut sheet can I believe? The Illuminating Engineering Society is an organization that creates and publishes standards for North America. The three standards that I have referenced here, IES LM80, TM21, and LM79, are critical for you to be aware of in your understanding of where these life ratings come from. LM80 is a standardized test methodology to test LEDs at different temperatures and at different currents. LM80 is used by the chip manufacturer. LM80 requires a minimum of 6,000 hours of test data, although longer times are certainly accepted. And also, 20 samples has become the standard sample size. There are provisions made in the standard to use fewer samples, but it then decreases the length of time that the existing data can be extrapolated out to estimate lumen maintenance. We move on to TM21. TM21 takes the 6,000 hour data accumulated in LM80 from the LED manufacturers in China and applies statistics to that data to actually extrapolate that data, meaning lumen maintenance data, out 6 times the burn time in LM80. So LM80 and TM21 are sister documents. TM21 requires the data from LM80. LM80 tells the manufacturer how to take the data. I mentioned LM79 because that is a document that's used by manufacturers of finished LED products. So LM80 is used by the chip manufacturer. LM79 is actually used by the lamp or luminaire manufacturer to measure performance, electrical and photometric, and then that data from LM79 is what's used on their cut sheets. Typically, LM79 data is done by a third party. In the case of General Electric, our lab is LM79 approved, so we can actually do our own LM79 testing and use the data taken here in-house in our cut sheets. Life ratings, traditional versus LEDs, is something that you've probably all seen and you're well aware of. These slides are really meant to illustrate the difference between a mortality life rating versus a life rating based on light loss or lumen maintenance. Mortality life ratings are applied to every light source other than LEDs. And by looking at the graph on the left side of the screen, you'll note that 100% rated life is reached when 50% of the product is still burning. This is true for fluorescent, HID, halogen, incandescent. What it means is that if you put in a large installation of lamps or luminaires, at rated life you can expect half the lamps or luminaires to have failed. That's why this is referred to as average life, or B50, meaning 50% failed at the noted time. LED life rating is not based on mortality, because what we find in our testing is LEDs don't fail. They just get dimmer and dimmer. So the industry has chosen a lumen maintenance curve to illustrate the life of an LED. Referring to the right-hand side of the screen, when the LEDs are brand new, they're at 100% lumens. As the lamps or luminaires burn, their light begins to drop. By 40%, you'll see it's at about 95% of initial. By 60%, it's at about 90% of initial. And at 100% rated life, per the IES, rated life is met, or 100% life is reached, when lumens have dropped to 70% of initial, or L70. So looking at the words at the bottom of the page, L70, B0, I mentioned that B50 on the left-hand side of the page means that 50% of the product will be failed at the rated life. L70, B0 means that at rated life, lumen levels will have dropped to 70% of initial, or L70, and there will essentially be no failures, or B0. This curve is generated by LM80 chip data, and once again, those chips are tested per that standard that we just mentioned on the previous page. This slide is meant to illustrate an important point. The LED luminaire or LED lamp is made up of the light source, which are the LED chips. They're connected to a printed circuit board, which is interfaced through many different materials to the heat sink. There's a driver that's taking your AC and making it into DC typically. There's going to be some kind of an optical system. There's going to be a housing. There might be some MOVs or TVSS built into the driver. There are many, many parts in that LED lamp or LED luminaire. And as we just spoke, TM21 is using simply LED lumen maintenance data to project life. This would be similar to you buying a computer which has the tower, which has numerous boards in it. It has a hard drive in it. It has a fan in it. It's got different drivers in it. It has a keyboard. It has a mouse. It has a monitor. If this computer had a life rating based solely on one particular metric, and in this instance, the metric of importance would be the enter key on the keyboard, then rating the life of this entire computer system on simply testing and evaluating and statistically extrapolating life based on a TM21 or similar document would be the same way that we rate the life on LED lamps and luminaires. The LED luminaire is based on lumen maintenance, extrapolated out 6 times the available data. And in this case, for our computer, this entire computer system would have its life rated on simply how well the enter key works. Now this may seem silly, but in reality, this is actually not how we do it for computers. Computers are tested for all the different parts, but LED fixtures are only tested for lumen maintenance life in many cases, and the life that's published for an LED luminaire or lamp is based solely on lumen maintenance based on LM80 and TM21 extrapolation. This is an important thing to know. Now the IES fully understand that rating the life of a luminaire or LED lamp solely on the LED lumen maintenance is not predictive of system life, and that's made very clear in TM21. However, on the street, life is rated on lumen maintenance, and typically there isn't a whole lot of conversation about anything else in the system. So whereas the computer is made up of many parts, so is the LED luminaire or lamp. And this is something I want you to consider as we go forward, talking about what does the life rating of an LED system mean. Let's talk about TM21. So TM21, you'll notice it's TM21-11, so that means that it was most recently published in 2011. And the title of the document is actually Projecting Long-Term Lumen Maintenance of LED Light Sources. That is its sole purpose. Looking at these 10 points, I'm hoping that reading through these it will help clarify what TM21 is and what TM21 is not. TM21 takes LM80 data and projects it using statistics to estimate light levels 6 times the available data. TM21 does not estimate the luminaire life. It simply is looking at lumen maintenance. The data that's being used in the statistical calculations in TM21 come from LM80, which requires 6,000 hour minimum burn time, and that data is taken in 1,000 hour increments. LM80 data is done at 2 set temperatures, 55°C and 85°C, and there's a third temperature that's done, and that's chosen by the manufacturer. So that can be between those two or below or above. TM21 requires a sample size of 20 pieces. If the sample size for TM21 calculations is less than 20, 10 to 19, then instead of being able to extrapolate out 6 times the test duration, the IES limit us to an extrapolation of 5.5 times the test duration. Because lumen maintenance changes over time, what's been found in the creation of TM21 is that the first 6,000 hours of data, so 0 hour, 1,000, 2,000, 3,000, up to 6,000 hour data, typically is not terribly predictive of long-term lumen maintenance. And if there is data that goes beyond 6,000 hours, then the data from 6,000 hours and below should be discarded and not used in the analysis. If data is available between 6,000 and 10,000 hour data, then only the last 5,000 hours of data should be used in the TM21 calculation. If 10,000 hour data is used, then only the last half of those measurements should be used, so 5 to 10,000. TM21 is doing its best with the data available to direct the manufacturer to come up with a statistically valid estimate of lumens at time. And the longer the LEDs are burned in LM80, 6,000 hours or further, the more likely that estimated statistical fit to the data will be meaningful. Number 9 states in TM21 that any data before 1,000 hours should be discarded. And then finally, something that's being done in the industry, and we'll get into this in the next couple slides, is that any manufacturer who is extrapolating beyond 6 times the test duration of the LM80 data, that life estimate is not recognized by the IES. And we'll start getting into reported versus projected or calculated life. And that's where some manufacturers are deviating from TM21 recommendations. This is a sample of some LM80 test data. You notice that the lower axis is hours of burn time in 10,000 hour increments. And then lumen maintenance is on your y-axis or your vertical axis. The data is taken at 55°C. I have an orange curve fitted here to the first 6,000 hours of data. So you'll notice that I have a bunch of blue dots in the upper left. Each one of those dots is an average of the 20 points taken. If I use TM21 to fit a curve to those points from 1,000 to 6,000 hours, discarding the first point, you'll notice that my output from TM21 allows me to state that I have L70 or 70% of initial lumens based on 6,000 hour data. That's what's in the parentheses. And the best I can say in this case is that my estimated L70 is going to happen at greater than 36,000 hours. How did I get to this spec? You'll notice that L70, which is down at the bottom of the graph, it's actually the x-axis, I hit L70 with this data extrapolated at about 52 or 53,000 hours. The problem is I only have 6,000 hours of actual data from my LM80 data. And TM21 says I can only extrapolate out 6 times my data set. So 6,000 hours times 6 is 36,000 hours. I did not hit L70 within my 36,000 hour window. I hit L70 at greater than 36,000 hours. In fact, I hit it based on this extrapolation at greater than 50,000 hours. Since TM21 doesn't let me extrapolate any more than 6 times my available data, using the TM21 protocol, the only statement I can make to be in concert with the IES guidelines is to make the statement that I have there. I hit L70 at greater than 36,000 hours. I can't say I hit L70 at 52,000 hours because that's exceeding the 6 times rule. So anytime you see a greater than sign in a life estimate, you know that the L number was hit at a level greater than 6 times the available data, and that's why I'm stuck with saying what I have here. Let's look at the green curve. Now the green curve actually takes us out to 10,000 hours worth of data. And per the TM21 guideline, I should use half of that data. So I'm going to use the 5,000 through 10,000 hour data to fit a curve. That's the green curve that you see. And I can now go as far as 60,000 hours, or 6 times my 10,000 hour actual data. And once again, I don't come anywhere near L70 on the graph that I have shown here. I'm hitting L70 well past 100,000 hours. But to stay within IES guidelines, the statement that I'm allowed to make is I hit L70 based on 10,000 hour data from LM80. Once again, that's what's in the parentheses, at somewhere greater than 60,000 hours, which is 6 times my available data. Any statement made past 60,000 hours in this case is considered unknowable. The data doesn't support it, and there's too much error associated with extrapolating out past 6 times the available data. So that's why, once again, in both of these cases, I've got that greater than sign in the statement that says that my L70 actually is occurring based on my extrapolation past my 6 times allowable extrapolation. Let me just run this by you one more time just to make sure this is clear. This is a little bit different than the last graph. So this is actually a set of LEDs. There's 20 in each point, so those triangles and squares. Let's look at it another way, and hopefully this will make it a little bit more clear. So this is a single instance where I have data taken on a group of 20 LEDs, each data point on the upper left. Each one of those points is actually 20 units averaged. That's actually the lumen maintenance at each one of those given time intervals. The IF, or forward current, through the LEDs is 350 milliamps. And given those two conditions, we're now changing the test temperature to 4 different levels: 55C, 70C, 85C, and 100 degrees C. You'll notice that the curves have different slopes. 2 of those curves are actually based on data. So the 55C and the 85C are based on the data. The 70 degrees curve is actually allowed by the IES, and it's actually interpolation between the 2 data sets. So the top curves, the red, the black, and the blue, are all within the IES guideline. Now I've added the 100C curve just to illustrate a point. Look at the upper right of the slide, and you'll note that I've made similar statements that I did on the prior slide. What I can say at 55C is that at L70, I'm going to be at greater than 60,000 hours. I can't go greater than 6 times my test data, so I'm stuck with saying that. If you look at your 55C curve, you'll note that that 55C curve is solid, and then it goes into dashed. It goes into a dashed line after 60,000 hours, and at that point the statistics don't support the curve. If I took that 55 degree line and ran it all the way out to L70, clearly my L70 would be greater than 100,000 hours. I cannot make that statement per TM21. Likewise, the black curve, or the 70C temperature test, can make the same statement as I can at 55C. I'm going to hit L70 at greater than 60. The 85C, likewise, within 60,000 hours, it does not hit L70. It's up around L80 at 60,000 hours. So I'm going to say that, once again, at 85C, L70, greater than 60,000 hours. Now I added in the green curve, the 100 degree C graph, to illustrate the point that in this case, I actually did hit L70 in less than my allowed statistical extrapolation of 60,000 hours. In fact, I hit L70 with the 20 units at 350 milliamps at 50,000 hours. And notice that in this case, I'm allowed to put an equal sign. So if I hit my L70 within 6 times my extrapolated data, the IES says I can use an equal sign. If I do not hit my L70 within the 6-time extrapolated data, then I have to use the greater than sign. I also want to bring up something that you all may be aware of, and it's something that the EPA put out a few years ago, actually in 2012, and it is called the Energy Star TM21 calculator. Now, the Energy Star TM21 calculator actually allows you to extrapolate your data from LM80 past 6 times, and by doing this, manufacturers are coming up with incredible life claims. So let's go with the 85C example on this page. Using the Energy Star TM21 calculator, I see that at 60,000 hours on the blue graph, the 85C, that I'm at about 80% lumen maintenance. Like I said before, I can say L70 greater than 60,000 hours. With the TM21 calculator, manufacturers are actually taking that blue curve and extrapolating it all the way out to L70, and they're making claims based on that that would say that their LED hits L70 at 87,000 hours. So they would make a life claim of L70, 87,000 hours. Now that does not comply with TM21 because they went past the 6-time limit, but you will see these calculated or projected life levels on many cut sheets in the industry, and it's up to the manufacturer how they want to use the statistics, but TM21 clearly states that you can't go past 6 times your maximum data. If you do, then it does not comply with IES, and the IES does not support that life rating. So be very careful when you're looking at life ratings. Are they actually reported life per TM21, which doesn't exceed the 6 times rule, or are they projected or calculated life, which does not comply with that IES standard? Let's move to a different subject. My computer analogy drove home the point that setting a life spec solely on a single component in a multi-component complex system may not make a lot of sense. Well, you know what? That's what we do all the time with LEDs. When we look at our failure data from our testing, we find that LEDs fail due to LED lumen maintenance. So that's really what I want to say, that, you know, when it hits L70, the LEDs are technically done. They need to be replaced. The system needs to be replaced. But we also find that in that LED system, which I have a photograph here on the lower right, there's a lot of other parts that can have problems before the LEDs hit L70. There can be wire bond failures. The driver, which can have many, many parts, can fail before that L70 number is hit. There can be color shift. There can be problems with finishes. Lenses can change colors. Gaskets and seals can fail, and water can penetrate fixtures. All of these failure modes prevent the end user from ever getting to L70. So their estimated life from L70 will actually never actually be obtained. So this is where I'm now deviating from TM21 and saying, if a manufacturer is solely basing the life of their LED product on TM21 calculations, and they are actually using the TM21 guidelines and reporting the data, they are in compliance with U.S. standards. If they are using projected or calculated numbers which exceed the 6 times rule in TM21, then they're kind of doing their own thing. And then there's a third option. How about if we rate the life of our LED product not only on lumen maintenance, but on the weak link in the chain? What is going to die first? What's the weakest item in my design, and therefore which item do I expect to fail first? And if that item fails before the LEDs hit L70, then shouldn't my life rating be based on the weak link, or the item that fails first, not on a projection of lumen maintenance based on TM21 or the projected calculated number? And my answer would be absolutely. It should be based on the weak link. When General Electric generates data for an LED product, be it a lamp or a luminaire or any other LED product that we sell, we do test the LEDs, we test the driver, we test the controls, we test opticals, we test finishes, we test housings, gaskets, we test any connections that are internal in the device. We test everything. From that testing, we generate reliability data for each one of those components individually as well as an assembly. Once we have all the reliability numbers for all the different parts, we can multiply those together and we can actually get the luminaire reliability. And what we found from our testing is that the weak link in any of our designs typically is the driver. And that's because the driver is the most complex device in the LED system. Some of our LED drivers on our commercial fixtures have hundreds of components. Those components are close to one another, they're mutually heating each other, they're complex electrical devices, and therefore they have the highest probability of failing first. So what we've done within General Electric is we've focused on the weak link in our system, and we've rated our products based on that. And in more than 50% of the cases of return product, the driver is what fails first. When we talk about driver failure, what we find is that it breaks into three different areas. It breaks into the infant mortality portion, which is usually during the first 1,000 hours. That we would call early life period or early burnout. And that would be due to manufacturing errors, shipping damage, installation problems, misapplications. Infant mortality is something we all kind of live with, and we all know that you get past that on the job and you move into the steady state period or the useful life period. And the useful life period spans the length of the rated life of the product for General Electric. So our useful life essentially runs out to the life spec, be it 15,000, 50,000, or 100,000 hours. Now during that useful life period, there's going to be a very low level of failures. And what we found from our testing is that low level of failure is somewhere between 0.05 and 0.10% per 1,000 hours. And that's at a 90% confidence level. That level of failures oftentimes is referred to as zero failures. But the reality of it is there is a finite number of failures that happen statistically, significantly less than HID, significantly less than other technologies, but nonetheless not zero. We hit rated life, which would be 50,000 hours, 100,000 hours, and at that point we run into a wear-out period or wear-out mode. And that is where the drivers start to fail, and they start failing rather quickly. Now if the product isn't at L70 when it hits this driver failure time, then that would be a time to replace the driver. And that's that green curve that runs off to the right. You go through your early life period, burn-in period, and then you have another useful life of your driver. If you're L70 and your drivers both hit end of life at the same time, that's the time that you replace the entire lamp or luminaire. So this bathtub curve is something that's used within statistics to graphically show what we expect to see with driver failures. Education is a key component in what we're doing here, and that's why y'all are watching this video, and I thank you for taking the time to do that. In addition to watching videos and going to lectures and going to classes, there's also a tremendous amount of paper material out there. The IES has many publications. There's a number of periodicals that can keep you up to date on what's happening in the industry. There's DOE documents. There's organizations that are publishing papers like the LRC, Lighting Research Center. There are many, many ways to stay up to date on what is going on in the LED industry. And what I want to talk about now is just a few of those specific items. The Department of Energy, the DOE from the U.S. government, runs two programs. They've been running these programs for years. And the first one I want to mention is called CALIPER. Now, CALIPER is an acronym for Commercial Available LED Product Evaluation and Reporting. And that program's been running since 2006. The CALIPER program is a program that is evaluating LED products' initial performance. So the DOE goes out and buys product off the shelf at retail or wholesale, bring them back to a third-party registered lab, generate caliper reports that compare the LED performance to the published ratings and the LED performance to incumbent technology. These reports are available to all of us free of charge by simply going to Google Caliper and pulling up the reports of interest. They're PDFs. They come in 3 forms. They come in application, detailed, and snapshot reports, and all of them allow us in the industry to become more knowledgeable about state-of-the-art products, what's working, what isn't working, and if you want, you can use the detail report and literally get down to the SKU, the manufacturer, how many they used in the testing, how many passed, how many failed, and literally look at numerous manufacturers, specific products, how they did in the testing. I think this testing is invaluable to someone who's trying to decide what is the right LED to put in my facility. Now, caliper is for initial performance. If you want to know performance long term, you would get into another DOE program, which is called the Gateway Demonstrations. Now, that was established 10 years ago, and it actually takes data out many years. Typically, it runs product out at least a year and a half. Others have gone even longer than that, and that's the long-term testing. Gateway reports come in 3 different versions. They're broken up really by segment. So indoor products, outdoor products, and specialty products. Since this is long-term testing, it really adds to the caliper program information and lets you find out how do these products work in actual applications, like in schools and hotels and on bridges and on roadways across the U.S. The last Gateway report that was published came out in September, and it had to do with changing color temperature inside a classroom and finding out how that impacted the students as well as the faculty. Very, very interesting report on the tuning of light in classrooms. It's something you might want to look at. So what separates GE from everybody else? You know what? It's real simple. It's testing, testing. Did I say testing? More testing. We do a lot of testing around here. And let me tell you a little bit more about that. GE does a tremendous amount of testing so that we know our products before we ship them. It is our obligation to make sure that the numbers we publish are real and they're based on actual data that has a strong statistical backup. Since LEDs last so long, we do a lot of testing that actually stresses these products well beyond what would ever be done in an actual application. This stress testing is done in very controlled chambers. It's done in various locations within our organization. And variables that are actually changed during this testing include such things as line voltage, ambient temperature, humidity, salt spray, and thermal shock. All of this testing is done to force the LEDs to fail early or the systems to fail early so that we can then predict what that system's life would be in an actual application. So if we're testing at 200 degrees Fahrenheit and we find that the system dies in 4 months, that same system run at 70 degrees Fahrenheit, given our statistical background, could last as long as 20 years. This sort of testing sets GE apart from the vast majority of other LED manufacturers. The takeaway from this is simple. GE tests to fail. Most other manufacturers test to pass. GE is testing in these chambers at extreme conditions so that we know our product before we ship it. We are not using our end users to learn about our life or our longevity. We know it before we ship the product. This puts us at a disadvantage because when a new product comes out, we need to test it literally for 9 months before we have enough data to say that it is going to have a GE monogram on it. But what that does for you is it lets you know that the product you're buying with that GE monogram actually has testing and quality built into it. And the numbers that you're relying on to make your decision are actually real. So in summary, if you're going to invest in LEDs, do your own evaluations. Bring product in. See how it looks. Put it in areas that are extreme. test it, find out if that product's going to look and work and give you what you need to light that space. There's a lot of blogs, there's a lot of public information out there on the internet. Read it. Find out what's working for people. Find out that isn't. Objective expert information from like the Lighting Research Center can be very informative to find out what is going on with LEDs, what's working and what isn't. National standards from the IES, we've talked about those, LM80, TM21, LM79. Those reports are very, very important to you so you know what is going into those products. And once the product's made, the LM79 report can tell you how it works. And those are done by third-party accredited labs so you can trust the data. Work with trusted designers, suppliers, and manufacturers. Everything we've spoken about today really matters to you, the buyer, to you, the specifier, to you, the designer, to you, the end user. Knowing that a product is actually going to work as stated, trusting the manufacturer, trusting the distributor, knowing the contractor, knowing the designer, all of these things come into play to make sure that a job is done right. Knowing that LED life is typically specified only for the LED, and that's based on 6,000 hour extrapolated data, hopefully gives you a better idea as to where LED life ratings come from. Also, comparing that approach to GE's approach clearly shows that we're doing it the right way. We're doing it the way you would do it if you were the manufacturer. We're making sure that before a product leaves our plant, it's going to work as advertised. And with our 5-year warranty, if something does go astray, we'll make it right. Even though it's written on a piece of paper doesn't mean that it's real. If you go through these items, realizing that testing really matters. I put in number 7 because of the changing world, the Internet of Things, big data. The fact that LEDs today are connected to the Internet and you can control them remotely, you can monitor their power. That is something that I also want to put in here as a means of tracking life. We can now literally look at the watts that's going into a fixture individually. We can monitor how many hours are on that fixture. We can now monitor and manage our lighting systems and track life in a way that we could never do before because of the connected intelligent functionality that's been added to so many of these systems. With that, I hope that you found this video helpful. This is the second in a series of LED videos that will be posted on GELearningCentral.com. As I mentioned, the first one that we did is LED Basics. This is our second, LED Reliability. I hope you enjoy it. Thank you so much for listening. This is David Korow at the GE Institute at Nela Park in Cleveland, Ohio, signing off for now.